Okay, this is Computer Science 305, Programming Languages, and this is ML3, Part 2. We're talking about function values and anonymous functions. Okay, so, pretty easy day, right? So there's lots of predefined functions inside ML, right? For example, you have ORD, right? Which, so these are, predefined variables that are bound functions. And so if we go, I think Control L, Control D, Control L. All right. So then we say SML. We'll open that up again. ORD, right? Which gives me that's ORD, and that gives us a function, right? That maps a character to an integer, right? So example, if we say ORD, and then the character C, right? I believe we saw this originally in ML1. What that gives is the ASCII value for that character. Okay. Interesting enough, this is also mapped, right? It's an integer to an integer. Basically, it's an operator that negates a given integer. So we can also, I believe, negate. It's also valued to not only just integer but real. When we define a function, right? The function, we see that the FUN notation for defining new named functions. You can also define new names for old functions using val, just as for other kinds of values, right? So we can actually define x as the negation operator. So we say val x equals the negation operator, right? Now we have an interesting function for that does this. So we can say x3, and that creates a -3. So, this is interesting. You don't see this in a lot of other languages outside of functional languages. So what this will do is it'll give us interesting capabilities for later on. So functions in ML do not have names, right? And we'll put that in italics, right? Just like other kinds of values, function values may be given one or more names by binding them to variables. The FUN syntax does two separate things, right? Not only creates a new function value, but it binds that function value to a name. So essentially, we could create anonymous functions without using the FUN keyword. So, for example, we create a named function as we have always done. We say FUN fx equals x plus 2, right? That creates a function f, right? So it's binding f to a value type of int mapped to int, right? Which then, if we execute f on 1, we get the value 3, as expected. We can also create an anonymous function, right? Just fn x equal, which maps to x plus 2, right? And what that gives us is some function fn, right? We can then use fn x. We can map this whole thing, right? So we're using this function defined literally in line, and then we're going to call it on 1, right? And that gives us 3. So that's how we do an anonymous function. Also, in some places called lambda expressions. So the FN syntax, right? Another use of the match syntax, right? That we saw from the previous video. What this allows us to do is we create a function expression by saying the keyword FN followed by a match. And so if you recall, a match is really just a rule followed by a rocket and then an expression. So we can use FN. Using FN, we get an expression whose value is an anonymous function. We could then actually assign that to something, right? We can define what FUN does in terms of val and FN, right? So FN, function, right? FUN, what it does is essentially it maps a val, right? What I was just saying is we could assign an anonymous function to a value. Well, if we did that, we're just doing FUN, right? It's the same thing as the next expression shows us, right? So if we have fun fx equals x plus 2, as we defined above, and we use val f equals fn x, and then we match that to create the match x to x plus 2, right? These are doing the exact same thing. Literally doing the exact same thing. So, as we can tell by looking in the entirety of the line here, which literally says the exact same thing we said right here. So, that's what it's doing. Now we know how it works. FUN is just a quick keyword for what it is that we're trying to do. So, now that we have that, we can use these anonymous functions all over the place. They actually become very useful if we need to use something right now really quick. We only need to use it once, or without having to do it outside of that exact area again, right? So it's for simple application. When you need a small function in just one place. So without fn, right, we'd end up having to define the function and then call it. For example, if we have some quick function like we're checking if a is less than b, if we didn't have fn, we'd actually have to define the function fun int before a b equals a is less than b, right? And then if we want to run quicksort, right? So quicksort takes in some list that we want to sort, and then the ordering for it. So 1, 4, 3, 2, 5, right, is our list, and then we're going to use this function we defined to perform the actual comparison. Right, we don't know what quicksort is, but if we had a quicksort defined, that's exactly how we would do it. On the other hand, if we had fn, we could actually do it without doing that by creating quicksort. I'm not going to actually write quicksort for us. I don't have time for that right now. But 1, 4, was it 3, 2, 5, 3, 2, 5, and then fn a b match to a less than b. All right, good times. And so that would actually work. But if we were to be able to do this, it would actually perform the quicksort. I'm not understanding why I cannot perform quicksort, but let's not worry too much about that. There's also the op keyword, right? So the op keyword so it gives us binary operators, our special functions, right? So if we were to say op star, it returns a function that has that takes an int by an int and returns an int, right? So it takes a two tuple of integers and then maps those to an integer, right? So the domain is a two tuple of integers, and the range is integer. Pretty simple for the base op, right? So we could actually use, if we were to do quicksort, we could actually use, instead of defining the function that was defined before, we could actually use op less than, right? And it would perform exactly as we expect it to. So sometimes you want to treat them like plain functions to pass. This just gives us the capability to treat them as a function rather than to treat them as a in-place operator. The keyword op before an operator gives you the underlying function. All right. So in the next video, we'll talk about higher order functions and currying, which are very important concepts for